Okay, time to prove using Boolean algebra that x or y and x or z equals x or y and z. Now, Boolean algebra proofs, just like any other proofs, can be simple when you see them done by somebody else. They can be frustrating when you have to do them for yourself, because you look at the proof and you say, oh, you said and 1 there. That's totally valid, but I have no idea how you knew how to do that. So first of all, I just want you to know, yes, these proofs can be frustrating to do yourself, just as proofs in algebra and geometry were probably frustrating for you in high school. At this point, though, the best way to gain the insight and to know exactly how to solve those problems is to see problems being solved. And so that's sort of what we're doing here, is we're giving you the experience of having seen at least one of these problems being solved. And here's the good news. We're not going to use a lot of Boolean algebra in electrical and computer engineering. Okay, yes, we will use Boolean algebra as a tool, but we won't be doing this sort of proof. We have many other tools that can help us to solve these. And just as the difference between an engineer and a mathematician is the mathematician proves things and the engineer applies them. We don't do a lot of proofs. We tend to do a lot of applications. So having said all of that, let's consider what is this equal to. Now I'm going to take x or y, and I'm going to AND that with x or z. I'm going to see, what is that equal to? Okay, well, that is equal to, I can distribute. This is that FOIL. And you can FOIL Boolean variables just exactly like you FOIL regular variables. So this is going to be x and x. Don't call it x squared, though. And we have or x and z, or y and x, or y and z. Okay, there's a couple of things that we're going to go ahead and do right off the bat. We're going to say x and x. One of our identities says that x and x is equal to just x. If it's 0 and 0 or 1 and 1, the second one really doesn't make any difference. We're just going to have x. I'm going to go ahead and keep this as x and z. I'm going to reverse these two, which is totally allowed. So I have x and y. Then I'm going to have or y and z. Now, this is one of those places where I'm going to say x and 1. We'll see why the and 1 in just a second. To be honest, I kind of had to back into that myself when I was working this proof out beforehand. I'm going to factor an x out of these two terms right here. So I'm going to say or x and the quantity z or y. So that's just a equivalency of factoring an x out. I'm going to keep the y and z down here. Now you can see that these two terms both start with x and something. So I can say x and 1 or z or y, or y and z. So this y and z term is really just along for the ride, and it will in fact appear in the final answer. That's where this y and z comes from right here. So it's just coming along for the ride. Now our job is really, you can see here, the other term is x. So I just need to find a way to reduce this down to just being x. Well, the first step in that is to remember that 1 ORed with anything is just 1. In this case, 1 is being ORed with z or y. It doesn't matter what it's being ORed with, it's just 1. So I end up with x and 1 or y and z. Anything ANDed with 1 is just that thing. So I get x or y and z. And so I have in fact proven that expression. This, by the way, was one of those expressions that was given as other Boolean equations in the lesson, and now we've actually seen it proved.